Let's now take a look at an example. So we're given some scalar field w, which is equal to x squared times y squared plus xyz. So notice there's no unit vectors, no directions in that. That's why we say it's a scalar field. And so we want to find two things. First, we want to find the gradient of this scalar vector, del w, and then we want to find the directional derivative, dw dl, in the direction 3 in our x direction, 4 in our y direction, 12 in our z direction at point 2, -1, 0. So we're going to start, of course, by finding that gradient del w. And so that's going to be useful because we can then evaluate that in the second part of our problem. So we need to know which coordinate system we're working in to use the appropriate equation. Of course, here we can see we have x, y, and z, and down here for this direction that we're doing our directional derivative, we also have x, y, and z directions, so we're using our Cartesian coordinates. So therefore we can say that this del w is equal to the partial of w with respect to x in our x direction, plus the partial of w with respect to y in our y direction, plus the partial of w with respect to z in our z direction. And so in this case, it's pretty simple. Just doing some simple calculus here, we get that the gradient of w is equal to, so first the partial of w with respect to x, we get 2x y squared plus yz. So all of that is in our x direction. For our second term, we have 2x squared y plus xz. That's in our y direction. And then finally, for our last term, we have just x times y, which is in our z direction. So this would be the answer to the first part of the problem. And again, keeping in mind, as expected, the gradient of our scalar field has resulted in a vector, or a vector field in this case. So let's move on to our second part. Now we want this directional derivative in a certain direction at a certain point. So we know from the previous video that in general we can say that this dw, this directional derivative dw dl, is equal to the gradient of our scalar field w dot unit vector in our L direction. Okay, so a couple of things we need to do. We need to evaluate our gradient at our specified point, 2, -1, 0, and we also need to define this unit vector u sub L. So let's start by saying at our point 2, -1, 0, we have that our gradient of w is equal to, and so the way we can find this is we're literally just taking our x value and plugging it in for all of these x's, our y value for all of our y's, and our z value for all of our z's. So simple as that. Doing that, we get that our gradient at that point is 4, -8, -2. And so let's keep in mind what this represents. This represents the direction of maximum increase, and if we took the magnitude of that, we would get the value of that maximum rate of change. Okay, so now what we can say is we can do dw dl is equal to, so we know this gradient at that point is 4, -8, -2. We're going to dot that with the unit vector, so let's kind of do this sort of in the middle of the problem here. So we have our direction of L was 3, 4, 12 given up here. So we have 3, 4, 12. And if we want to make that a unit vector, we just divide by the magnitude. So we have 9 plus 16 plus 144 for our magnitude. And so that turns out to be 4, -8, -2 dot with 3 over 13, 4 over 13, and just using fractions here to keep everything exact, and 12 over 13. So if we do that dot product, we find that our directional derivative in the direction of L is equal to approximately -3.385. Okay, so it's actually sort of in the opposite direction of the maximum rate of increase, which sort of makes sense if we stop to think about it for a little bit. So our direction of L, as we can see up here, is 3, 4, and 12. However, at this point 2, negative 1, 0, we saw that our gradient is in the direction of 4, negative 8, and negative 2. So our y and our z directions are opposite. So if we're trying to find that directional derivative in L, we're basically going sort of opposite from the direction of the maximum rate of increase. And so as I stated before, if we wanted to find our max rate of increase, we can find the magnitude of that w. So the magnitude of our gradient. So max rate of increase, and that's at a specific point, so 2, negative 1, 0, is basically going to just be square root of, so we're finding magnitude of this guy, so 16 plus 64 plus 4, and that ends up being about 9.165. So we can see this would be the maximum rate of increase, but when we go in the direction of that L vector, we have negative 3.38, so we're actually decreasing in that direction. Okay, so a couple of things I want to point out now. So if you want some more practice with the gradient, you can look on page 73 in your textbook, example 3.3. And so in that example, there are actually some problems with cylindrical and spherical scalar fields as well, so that could be some good practice. But one thing I want to do is point out a useful trig identity. The reason I want to point that out is because in the textbook, the author just kind of assumes it's common knowledge. But I know at first I had a little trouble when I was looking through this because it has been a while. So if we have the derivative with respect to theta of sine squared of theta, that actually equals 2 sine theta cosine theta, which is equal to sine of 2 theta. And so this equation is probably something good to have on your note sheet or somewhere that you can reference quickly while doing homework and things like that. So while it's not relevant for this example, let me go ahead and put down a couple other useful trig equations or identities. So remember, of course, we have sine squared of theta plus cosine squared of theta is equal to 1. And we also have cosine squared of theta minus sine squared of theta is equal to cosine of 2 theta. And so, of course, these trig identities are going to come into play as we're dealing with our spherical coordinates. We've got a lot of those sines and cosines floating around.